Related rates require that you get a really good visual. So for this one, we got part of the picture, but you really need to get in the habit of getting the visual, drawing the picture if you're not given anything. I think that's part of the battle, and that way we can basically apply variables in the right spots and make sure that we have everything lined out and organized well. Okay, so we're reeling in a fish, and that fish is being reeled in at a constant rate of 2 feet per second from a bridge 16 feet above the water. Okay, at what rate is the angle between the line and the water changing? And then here's my freeze frame moment when there's 20 feet out of the line out. So you've got part of the picture, but you really need to complete this. Remember, ultimately what we are looking for is we're saying that here's the fishing line, because we're standing up here. This is where we're standing. Okay, and we're reeling this in. So here's my fishing line. We love right triangles. Love, love, love them. Okay, we can use Pythagorean theorem for some pieces, and obviously we can use sine, cosine, and tangent if we're being asked about angles. So this is the line, right? And I need a label for all of this. My habit is to label these as x, y, and z, and I usually tend to do z for the hypotenuse. If you're not a fan of that, do a, b, and c. That's fine. But get a label down so we can go through the process of organizing our information. All right, so I know that the fish is being reeled in at a rate of 2 feet per second. So what that means is that this is changing at 2 feet per second. All right, so dz dt is what I am being asked, or what is changing at 2 feet per second. Then it asks what rate is the angle between the line and the water. So that is theta. So I'm being asked to find the theta dt. Okay, that is my I don't know. I have no idea what's going on there. So again, same organization. That's my question mark. What is fixed? What is not changing? Well, the first thing is, like, I'm always going to be at 16. Okay, x is equal to 16. That's going to hold true. I'm always going to be 16 feet above the water. The other thing that's not changing is that dz dt is going to be equal to negative 2 feet per second. And the reason I put the negative on there, I don't want you to freak out about that. The reason I put the negative on there is because it's coming back to me. All right, so it's not going further away from me. It's going back to me. So technically, it's going to be a negative 2 feet per second. If you don't have the negative on there, you're still going to get the same answer, but you just need to recognize what's happening. All right, my freeze frame moment is going to be when there's 20 feet of line out. So when z equals 20. That's a z. Sorry, let me get that. There we go. So when z equals 20, that's why I do my labels. All right, so I don't have to put when the line out equals 20. I can just put when z equals 20. Okay, so this one's a little different because it has that theta involved in it. So if I am trying to figure out this theta and how fast this is changing, I have to make sure I use information about the stuff that I've been given. Okay, I can't grab information about this. Why? Because I really don't know much about it. But I do know a lot about z, and I know that that's going to stay the same. So I want to use a trig ratio that includes these two. Now, technically, okay, you could use cosecant because that would be the hypotenuse over the opposite. But why would you do that when you can use sine, which is opposite over hypotenuse? All right, so that's going to be my equation that I set up. I'm going to do sine of theta is equal to the opposite, which is x. But remember, 16 is fixed. It doesn't change. So I can go ahead and plug in a 16 there. So 16 over z. Now, z is changing, so I don't want to mess with that too bad. All right, when I take my derivative of this, my derivative work here, I'm going to say the derivative of sine is cosine. So cosine of theta, again, it's implicit, so d theta dt, that's what I'm trying to find, is equal to, now I would recommend that you rewrite this as 16z to the negative 1. Because now I don't have to do a quotient rule. All right, I can just drop the negative 1 down, and then I can subtract 1 from the exponent. So I end up with negative 16, and then that would be z to the negative 2, so I'll go ahead and move that down as well. But remember, this was implicit, so I have to have dz dt. Now, I put lines on my z's. If you don't like your z's, then that's fine. You can, like I said, you can use a, b, and c, but you should have something comparable to this. Okay, now I have dz dt, I have a z. This is kind of my biggest concern, because this is what I'm looking for. Cosine is going to be adjacent over hypotenuse. Well, I know that z is going to be equal to 20, but I know nothing about this. We love right triangles, because what it means is that I can go back and I can use this piece of information that z equals 20 and x equals 16, and I can actually, let me actually write it out one more step. We can say x squared plus y squared equals z squared. So at this when z equals 20 business, 16 squared plus y squared equals 20 squared. And then I just go through my process of finding y. All right, so this would be y squared is equal to, I would subtract 16 squared, I would end up with 144. So y is equal to 12. So when z equals 20 is also when y equals 12. Those are the exact same moment in time. Okay, so just recognize that those go together. All right, so I'll go ahead and plug in my values for cosine. So cosine of theta is going to be the adjacent over the hypotenuse. So adjacent was 12, hypotenuse is 20, d theta dt. And then I'm plugging stuff in over here as well. So negative 16z squared, I'll just go ahead and write it as that. And then dz dt was given to me as negative 2. Okay, now remember I'm solving for d theta dt. So I want to know how fast that angle was moving. So I would be multiplying by the reciprocal. So I'd have negative 16 over 20 squared times negative 2 times 20 over 12. That's the reciprocal of this. Okay, so that's like doing this. So I have to multiply on this side as well. Now the reason I haven't multiplied anything out is because I can see that that 20 and one of these 20s will go away. All right, so that'd be like 20 over 400. All right, so sometimes it's easier to keep that, sometimes it's not. I could also reduce 16 and 12. That would be a 4 over 3. And I would prefer to reduce before I multiply just because it's going to make it easier on me, especially if this is on a non-calculator section, which is very possible. All right, so this would end up being, let's see, let me reduce this, negative 8 over 60, looks like. So both of those are divisible by 4, so it would be negative 2 over 15. Now I do need a unit, so because this is a theta, it's going to be in radians. Radians refers to the distance. This is not in degrees. All right, we are dealing with lengths, so we're dealing in radians per second, I believe. Let me go back to the equation. Yep, so we're dealing in feet per second. Okay, so I would have to go back and say this is going to be in radians per second. Now, please don't give this to me in feet per second. If you are dealing with a theta, you have to consider this as radians. Now the time is the same, but this is in radians per second. All right. So we use two different equations to help us with this. We use Pythagorean theorem to get my other freeze frame moment. Okay, and then we also use the trig ratio to actually work through my derivative work. All right, this is pretty common for us to have to do maybe an extra step to find a piece that's missing at that freeze frame moment in time. But Pythagorean theorem is pretty common, so just be aware that you can use that and probably will use that pretty often.